So good morning to everyone. So good morning. Yes. Good morning. So we will wait for another 1 or 2 minutes. Then we'll start with the class. Okay? So good morning. Tiffin, it's done. Spurti. Yes. My breakfast is over. So someone is asking when will be CS class? Okay. So it will be announced as soon as possible. But before starting with the today's concept, as usual, we'll go with brief discussion about the previous class. Okay. So what and all we have discussed in the previous class? So we have discussed about types of what we have discussed? Types of catalyst. So we have discussed about the types of catalysts. So on what basis this classification has been done? Based on their miscibility with respect to, or based on their interaction with respect to reaction mixture. So whether they are miscible in the reaction mixture or they are immiscible in the reaction mixture. So based on that, they have classified the catalyst as homogeneous catalyst and heterogeneous catalyst. Right? So that's where we have the types of catalyst. So one is homogeneous catalyst and another one is heterogeneous catalyst. Now what do you mean by homogeneous? So catalyst and the reaction mixture, they are in the same phase or they are miscible with each other. So heterogeneous catalyst means where catalyst and reaction mixture, they are immiscible with each other. That's where they are in the different phase. So that's where we have the two types. Now when it comes to the example for each, which we have discussed in the last class. Now when it comes to heterogeneous catalyst, when it comes to the mechanism, one of the example which I took for explaining the mechanism here is, that is with respect to Haber's process, where they will be using iron oxide powder, so which are solid in state. So therefore it is heterogeneous catalyst. Now in mechanism we have discussed how adsorption is going to play the role during the catalytic mechanism, where a reactant which will be gaseous in nature, reactant will diffuse towards the catalyst surface. So first one is diffusion of reactants towards the catalytic surface. Next one is adsorption. Next step is adsorption, where these reactants will get adsorbed to the surface of the catalyst. Next one, that is dissociation of the molecule atoms. They will convert it into individual atoms. Next one is interaction among these atoms. Interaction among these atoms. So once the interaction happens, there will be formation of product. So due to the interaction, there will be formation of product. So what is next step? This product will get desorption. Next step is desorption. That means whatever product has been formed, it will diffuse away from the surface of the catalyst. So these are some of the steps with respect to heterogeneous catalyst, not with respect to homogeneous. Okay na? So this is exactly better explainable for heterogeneous catalyst. So that's what we have discussed in the last class. Fine. Now, when it comes to solid surface, now in the last class, as I have told, we have discussed the mechanism. In that way, with respect to the last class, we have discussed all this mechanism. Now we will discuss about nature, how this catalyst, that is solid catalyst, they are going to have the function. Now one thing here is they will help in the activity of the reactants, or they help in the reactivity of the reactants. So that is one thing. That's what I have explained, where hydrogen molecule will get dissociated into hydrogen atom, nitrogen molecule will get dissociated into nitrogen atom. That's what we had discussed, right? Now what will happen? They will dissociate, and even this one will be dissociate. Now that's where they are going to interact with each other, and there will be formation of the product. That's where they helps in the activity of the reactant. Okay na? Next one, they are having specificity. Yes, they are having the specificity. Now when I am talking about the Haber's process, naturally iron oxide will be the good catalyst or heterogeneous catalyst for the reaction, where nitrogen and hydrogen will react with each other to form the product. Now for example, I have carbon monoxide and hydrogen. I am taking the example of your textbook itself. So which will get converted into methane and water. So exactly opposite reaction in the last class or previous class I have discussed. Now carbon monoxide and hydrogen will react to form methane and water. Right? Now whether equation is balanced? No. So here it will become 3. That's where we have the equation. Now this reaction, where carbon monoxide will react with the hydrogen to form methane and water in the presence of nickel. In the presence of nickel. If I do the same thing in the presence of copper, if I do the same thing in the presence of copper, there is no question of formation of methane. In the presence of copper, there will be formation of formaldehyde. There will be formation of formaldehyde. Now reactants are same. So carbon monoxide and hydrogen in presence of nickel as the heterogeneous catalyst, there will be formation of methane and water. Same molecule, carbon monoxide and hydrogen, in the presence of copper, they will form formaldehyde. So what it indicates? It indicates that although they are heterogeneous in nature, we cannot imagine that they are only providing the surface. So along with that, they have the specificity also. Right? So if you change the catalyst, definitely the product will be different. So that is where they are going to involve in the reaction of these elements. Okay na? So that's where there is a presence of specificity with respect to the heterogeneous catalyst. Fine. So these are the nature of the heterogeneous catalyst. Any doubts? Now, once it is done, we have another type of catalytic mechanism, that is with respect to shape selective. Next one is shape selective catalysis. Shape selective catalysis. Now in the name itself it is there. Based on the shape, selection will happen. So based on the shape, selection will happen with respect to the catalyst. So shape selective catalysis means these are the reactions where catalyst will do its function based on the shape of the reactant. Based on the shape of the reactant. One of the very good example is zeolite, which you people have discussed in first year class about the zeolite with respect to group 13 and 14 elements. That time you have discussed even with respect to group 1, because this zeolite is nothing but sodium aluminium silicate. So it is nothing but sodium aluminium silicate, right? So that's where we have the zeolite. That's where we have sodium aluminium silicate. Now this particular molecule or this particular compound, speciality of this compound here is they will have pores in their structure. They will have the pores in their structure. Now depending on the size of the pore, they can take up only those particular reactant which can fit into these particular pores. Yesterday somewhere they were asking whether reactant will bind to interstitial space. So that's where we have got the example. That's where I told it comes under shape selective catalyst. Now this zeolite, as we know, one of the application is with respect to conversion of hard water to soft water. If you recollect first year hydrogen topic. So that's where one of the method for conversion of hard water to soft water. Same with this zeolite can also be used in cracking of petroleum products. It is used in the cracking of hydrocarbons or petroleum products. So there also based on the size of the molecule, it can accommodate those molecules in its crevice or in its pores, and that's where reaction will happen. So zeolite is one of the best example for the shape selective structure, okay na, or shape selective catalysis, okay na. So someone had written comb like, honeycomb like structure. Yes, it will be having the honeycomb like structure. So what is that honeycomb? So that is nothing but ಜೇನುಗೂಡು ಕನ್ನಡದಲ್ಲಿ ಹೇಳಬೇಕು ಅಂದ್ರೆ, ಓಕೆನಾ. So that's where we have the honeycomb type of structure. So that's where based on the shape and the size of the catalyst, it can be accommodated in those particular pores and the reaction will happen. Fine. So now we will move to the next one. Whatever I have discussed all this time, it was related to heterogeneous catalyst. It was related to heterogeneous catalyst. Now I am coming to the enzymes. Enzymes as a catalyst. Enzymes as a catalyst. That means enzyme is nothing but catalyst only. So which will be called as biocatalyst. Enzymes will be called as biocatalysts. Right? So now why they are called as biocatalysts? because they are going to catalyze. They are going to catalyze biological reactions. Biological reactions. So which can be called as biochemical reactions. Which can be called as biochemical reactions. Now all of us we know, biology students, they have got the answer. Now, what do you mean by bio? Bio is nothing but life. Now, biochemical reaction or biological reaction means these are the reactions which takes place in the living cells or living organisms. So that's what they are called as biocatalyst. Haber's process, where nitrogen and hydrogen getting converted into ammonia. In Haber's process, where nitrogen and hydrogen, they are getting converted into ammonia. It is not an example for biological reaction. It's not an example for biological reaction because those reactions will not take place in our body. Right? In living organisms it will not take place. I am talking about Haber's process. Yes, some of the bacteria, they can convert nitrogen, hydrogen into ammonia. That is not considered as Haber's process. I am talking about Haber's process only. So like that, some of the reactions which takes place outside the living system. So they are not considered as biological reaction. Biological reactions are those which takes place in the living system. So for those reactions, enzyme will be playing as a catalyst. So for those type of reaction, enzyme will be playing as a catalyst. That's where we have the enzyme as a catalyst. Due to that, we have to discuss about the enzymes because these are abundantly present in the nature with respect to in our body or with respect to in the plants or with respect to the bacteria. Everywhere these enzymes are present. Different types of enzymes with respect to different reactions. It's clear? So that's where we have the enzymes. Why we have to discuss about the enzymes? This is the reason. Now when it comes to nature of the enzymes, now one important point here is these enzymes, they are specific. As solid as a catalyst I have told. In carbon monoxide and hydrogen, they will convert it into methane and water in the presence of nickel. Right? Same nickel can also be used when alkene is given for hydrogenation. So what I mean to tell here is, when it comes to solid as a catalyst, where carbon monoxide and hydrogen, nickel is there, which will get converted into methane and water. Right? So this is one reaction which we have already discussed. Same way, in another case, where it can be nickel can be used is hydrogenation of alkene. Right? There is a specificity, no doubt. But what I mean to tell here is nickel can catalyze more than one type of reactions. It's not compulsory that nickel is going to involve only in this reaction. No. Nickel can also be used for hydrogenation process also. Like palladium, which will be used for hydrogenation process. So what I mean to tell here is, when it comes to solid as a catalyst, specificity is there, but they are not very specific. More than one reactions, some of the metals can be used. But when it comes to enzymes, they are very specific. They are very specific with respect to the reactions. They are specific with respect to reactions. That means with respect to reactants. They are specific with respect to reactants. If I want to have the example, I will take same one. Yesterday someone had told, I remember now. Someone had written invertase. I will take the same example. So when I am talking about invertase, which is going to act on the molecule sucrose, which is involved in the hydrolysis of sucrose. Invertase can also be called as sucrase. It can also be called as sucrase. One and all same. Sucrase and invertase, one and all same. Same enzyme. C6H12O6. C6H12O6. That's where I have got glucose and fructose. Now, if you see this reaction can be catalyzed only by the invertase. No other enzymes can act on this. No other enzymes can act on sucrose for the hydrolysis of sucrose. Now, whether sucrose can be hydrolyzed only by this? No. Sucrose can be hydrolyzed by many other methods. For example, if I expose this sucrose for the acidic condition, not very high concentration, so in the presence of sulfuric acid, once again it can be converted into glucose for plus fructose. But what I mean to tell here is, enzyme, if you are going with enzymes, then sucrase is the only enzyme which can play this role. That's where there is a specificity. Now I can tell we have another molecule, maltose. So we have another molecule. Everything you are going to discuss in your biomolecule topic. So this maltose will act by the enzyme maltase to give rise to glucose and glucose, another disaccharide. Now why I have written this reaction? Because maltase is specific for maltose, sucrase is specific for sucrose. Maltase cannot act on the sucrose, sucrase cannot act on the maltose. Although sucrose and maltose, they are disaccharides. They are similar molecules. I am not telling they are same. They are similar molecules. But still, these enzymes will discriminate between these two reactants. So therefore, I have given this statement as enzymes are very specific with respect to reaction or with respect to reactants. That is a very important feature of the enzymes as a catalyst. Now, when it comes to the enzymes, as I have told, they are present with respect to living system. They are present with respect to living system. Now, many enzymes, I am not telling all the enzymes, many enzymes, they require optimum condition. They require optimum condition. Now, as I told, many enzymes, they require that optimum condition can be where pH should be somewhere around 7.4. One of the optimum condition is pH should be somewhere around 7.4. Now, temperature can be somewhere around 37 degrees Celsius. Temperature will be somewhere around 37 degrees Celsius. Right? So what I mean to tell here is, if you observe the condition, whatever I have written, biology students, already they got the answer. Whatever I have written, it is related to our system, human body or living organism condition, where our blood is having pH somewhere around 7.2 to 7.4. Human blood, 7.2 to 7.4. Our body temperature, right? It can be 98 degree Fahrenheit or 37 degrees Celsius. So that's where I have got the condition, optimum condition. Many enzymes falls under this category. Many, not all. Once again I am telling not all. because we have some of the enzymes which acts in our stomach. Now, biology students should tell me what is the pH of the stomach. Any biology students here? What is the pH of the stomach? Anyone? Okay, any answer? pH of the stomach. pH of the stomach is somewhere around, okay, someone has written 1.5 to 2. Yes, we can take it as 2. Somewhere around 2. Now at that particular temperature we have one enzyme which is called as pepsin, which will be active. Pepsin requires optimum condition where pH should be not 7.4, pH should be acidic, that is around 2 to 3. So that's why they are active at acidic pH. But most of the enzymes, they falls under this category where pH should be 7.4 and temperature should be 37 degrees Celsius. Right? So therefore, we have a terms like optimum temperature. We have the word like optimum temperature and optimum pH. Okay. So now optimum temperature is also applicable for any other catalysts also. Optimum temperature can be applicable for any of the catalysts, not only for enzymes, but we will focus on the enzymes. Now when I am talking about optimum condition, so what I mean by optimum condition? It is the condition at which a given enzyme will have the maximum catalytic activity. That's why I can define. Now, what is optimum temperature? Optimum temperature is the temperature at which a given enzyme will have maximum or optimum activity. Same logic is applicable or same definition is applicable for optimum pH also. Fine. So what I mean to tell you is when I am talking about first character of the enzymes, they are very specific. Second one, they require optimum condition for their activity. Which are those optimum condition? With respect to pH, it can be somewhere around 7.4, and with respect to temperature, it can be somewhere around body temperature. With respect to humans, I am talking about. Right? So that's where we have very important two nature of the enzymes. Now, another nature of the enzyme here is they requires additional elements which I can call it as promoters. Yes, now I can call it as promoters. Now here I can call them as cofactors. I can call them as cofactors. They require additional elements for that activity. So that can be either magnesium ion, which will be utilized for its activity, enzymes activity. Some of the enzymes they demand for their activity cupric ion. Say for example, we have an enzyme called as kinase. I will not go in detail. We have an enzyme called as kinase, which is very much dependent on the magnesium ion for its activity. Which is very much dependent on the magnesium for its activity. It may helpful for your NEET exam. That's why I am telling all these things. Okay now? So same way we have some of the enzymes like superoxide dismutase, SOD. They will call it as SOD. What is SOD? Superoxide dismutase. They demand copper for their activity. They demand copper for their activity. That's where we have the cofactors. They require additional elements for their activity. Right? So these are some of the examples for the cofactors. Now, along with that, as we have discussed, even enzymes will get inhibited by using inhibitors. Enzymes activity will get inhibited or enzymes, it will going to lose its activity in the presence of inhibitors. Now, for example, I can take hemoglobin as an enzyme. What is that hemoglobin is doing? Hemoglobin is a protein present in our blood, involved in the transportation of oxygen, exchange of oxygen in the tissues. So that's where I have the hemoglobin. As we have discussed yesterday's class, this hemoglobin activity will be inhibited by carbon monoxide. Hemoglobin activity will be inhibited by carbon monoxide. That's where we have the cofactors, which can also be called as activators. Then we can have the inhibitors, right? So that's where we have the nature of the enzymes. But important one here is they are very specific, and second one is they demands optimum condition, like optimum temperature and optimum, and then optimum, no answer, all are silent today. So that's where optimum pH and optimum temperature they demands. Now in addition to that, even they requires cofactors, that is activators and inhibitors, which is going to inhibit. Yes, optimum pH. Yes, okay now. So hagadre we have one model which explains why these enzymes are very specific in their activity. One model is there which is called a hypothesis, lock and key hypothesis, lock and key hypothesis. Okay now. Now when it comes to the lock and key hypothesis, in the name of the hypothesis only it is that if I take this one as an enzyme, if I take this one as a enzyme, okay, now enzymes will have one particular pocket type of structure which are called as active sites, which are called as active sites. Once again, these things we are going to discuss in chemistry in everyday life. Last chapter of organic chemistry, second period. So we have the enzymes. All the enzymes will have pocket type of structure which are called as active sites. Now I can define the active sites. These are the part of the enzyme. These are the part of the enzymes which helps in binding to the substrate, which helps in binding to the substrate. What do you mean by substrate? Substrate is nothing but reactants. In a regular chemical reaction, we used to call them as a reactant. But when we are talking about enzyme catalyzed reaction, we'll call reactant as a substrate. Got my point? So that's where I have got the substrate. So active site is the part of the enzyme, not whole enzyme. It is the part of the enzyme which helps in binding to the substrate. Now, for example, I have two types of substrate. This is substrate 1 and another one is substrate 2. Now, based on the shape of the active site, which particular substrate can fit into the active site, whether S1 or S2. Based on the shape of the active site, you should tell me among these two substrates which is exactly going to fit into the active site. So naturally people are giving the answer, that is S2. Very good. So that's where we are going to have the enzyme occupied with the substrate, right, which is called as ES complex. This is nothing but ES complex. What is ES complex? Enzyme bound with the substrate, that is nothing but ES complex, which later converted into E plus P, that is product. P is nothing but product. For the product formations to happen, ES complex has to be formed. So now, if I imagine enzyme as a lock and substrate as a key, so that's where each key is going to fit into a particular lock only, or each lock can accommodate a particular key only. So that's where lock and key hypothesis talks about specificity of the enzyme. What is that lock and key hypothesis talks or explains? It explains about why there is a specificity in the enzyme catalyzed reaction. So that is based on the shape of the active site, which is going to decide which particular substrate it can occupy. Fine. So that's where we have the lock and key hypothesis. Any doubts? Now if you observe, once again there is adsorption, right? Where surface of the enzyme is taking the substrate. Once again it is nothing but adsorption only. Like substrate with reactant with respect to solids, heterogeneous catalysis. We have discussed, right? Same way it can be adsorption. So therefore adsorption phenomena can be observed in almost all the catalytic reactions. Fine. So that's where we have the lock and key hypothesis. Whether I am clear? Any doubts? Because by this we are done with the catalysts and catalysis. We are moving to the next concept. We are moving to the next concept, that is colloids. That is nothing but colloids. We are moving to the next concept, that is nothing but colloids. Now, any doubt with respect to catalyst and catalysis? If you don't have any doubts, we will move to the colloids. Shall I start with the colloids? Now, when I am talking about the colloids, for example, I have milk. Day-to-day life example only I will take. I have milk, not spoiled one. A good milk is that, a fresh milk, which I have kept it in a glass for 1 hour. I have kept it in a glass for 1 hour. And all of us we know it will be having white color. Milk will be having white color. It will not be crystal clear. That means what I mean to tell here is, if I take a glass of milk, if I hold it in front of my eyes, I cannot see other side of the glass. Right? So that's where I can tell that solution is not crystal clear. Right? So that's where I have the milk sample. Now I will keep it for 1 hour. I will keep it for 1 hour on the table. Right? Now in the same way, I will have salt plus water. I will have salt plus water. Now they are present in once again glass, similar glass. Right? So to indicate something is there, I have written the dots. Now all of us we know that when I will put salt into water, when I will hold that glass in front of my eyes, naturally I can see on the other side. Naturally I can see on the other side of the glass. All of you will agree? Now I can see other side of the glass without any hindrance. Therefore they are called as crystal clear solutions. They are called as crystal clear in nature. Now I will take another example where soil has been added to the water. Soil has been added to the water. Once again I will have solution. Right? Now I will keep it for 1 hour. I will keep it for 1 hour. Now you should tell me what will happen with respect to 3 conditions after 1 hour. What will happen for these 3 after 1 hour? First one is milk, second one is salt with water, and another one is soil with water. This is first one, second one, third one. So you should tell me what will happen to glass after 1 hour. Okay. Milk remains the same. Very good. Milk remains the same. No doubt. Very good. So it will remain same. That's what I told. I am not talking about spoiled milk. I am talking about fresh milk. Yes. It will remain same. No change in anything. So now what will happen to salt plus water? Naturally, even this will remain same. But if you go with the last one, if you go to the last one, now there will be formation of two layers. Now there will be formation of two layers. Upper one will be bit clear solution, but lower one there will be precipitate. There will be precipitate of salt. There will be precipitate or deposition of salt at the bottom. Or I can tell, rather than precipitate, I can tell deposition of the salt which takes place at the bottom. So what is happening? So it is remaining same, it is also remaining same, but here no, there is a difference compared to first and second, right? So that is majorly because if I take size of the particles which are present in the milk, because milk is a solution, no doubt, milk is a solution which is made up of many proteins, sugars in the water. Milk is a solution where many proteins, sugars are present in the water. So milk is a solution, no doubt. Salt is also a solution, as all of us we know, where salt is added to the water. Now soil plus water, yes, it is also a solution only, where soil particles are added to the water. But the problem here is, with respect to last one here, is the size of the soil particles is large. Size of the soil particles are very large, and size of the salt molecule is very small. It is very small. When it comes to here, size of the protein and sugars, they are moderate in size. They are moderate in size. Large, very small, moderate. So that's where I have got the colloidal solution. This is nothing but colloidal solution. Right? That's where we have got the colloidal solution. But please remember, this is not a colloidal solution. So this cannot be a colloidal solution where particle size is very large. They are getting precipitated or they are getting deposited after some time. But colloidal solution, they are not going to get settled down. They will remain in the solution. That's where we have the colloidal solution. In that way, what is that difference between pure homogeneous solution and colloidal solution? Now what I mean to tell here is, I have got homogeneous solution. I have got homogeneous solution. Next one is colloidal solution. And the last one is heterogeneous solution. Heterogeneous solution. Now, as I go with the example, salt plus water is homogeneous solution. Whichever part of the container I will take the solution, concentration of salt will remain same. There is no difference. At least at my home, if I prepare salt solution, if I take from the top or if I take from the bottom, taste will remain same. Whether same thing is applicable for at your home also, or there is a difference. So it should remain same. Okay na? So therefore they are called as homogeneous solution. Now this is where we have the heterogeneous condition, where at the bottom soil particles are more compared to the top. So therefore there is a variation in the concentration. So therefore it is an heterogeneous solution. Now colloids, yes, whichever part I take, concentration of protein and sugar, it will remain same. That's where we can say with respect to milk, right? So therefore, when it comes to colloidal solution and homogeneous solution, there is no difference with respect to concentration. It will remain same throughout the container. But the difference here is size of the particles. This will be crystal clear, they will not be crystal clear. So therefore, if I take the size of the particle, I can arrange like this. I can arrange them like that, where there is an increase in the size of the particles as you are moving rightward direction. As you move in the rightward direction, there will be increase in the size of the particles. So that's where we have the colloidal solution, right? So what are colloidal solution? These are the solution which are made up of colloids. So these are the solution which are made up of colloids. They are called as colloidal solution. Now when I am talking about colloids, size of the colloids, when I am talking about size of the colloids, they can range from 10 to the power of minus 9 to 10 to the power of minus 6 meter. They can range from 10 to the power of minus 9 to 10 to the power of minus 6 meter. This one you should remember. Okay? So 10 to the power of minus 9 to 10 to the power of minus 6 meter I am telling, not nanometer or millimeter. Okay now? So unit is important. Now anything above this size, then heterogeneous solution, where particle size will be large. Anything above this, anything below this, then homogeneous solution, right? Any particles with this range, size with this range, then they will form colloidal solution. So what is the size range of the colloidal particles? That is 10 to the power of minus 9 to 10 to the power of minus 6. Someone had asked something, that question disappeared. 1 minute. Okay, so Brinda, large particle will settle down, light particles float. Okay, okay, Brinda, sir, we can see Tyndall effect in colloids. Okay, done. So that one will have a discussion with respect to nature of the colloidal solution. Yes, definitely. We are going to discuss all those things, and it's bit important, Tyndall effect. Okay, but before going for that, these are with respect to the nature of the colloidal particles. Now very important point here is size of the colloidal particles. Which is that one? The range, it ranges from 10 to the power of minus 9 to 10 to the power of minus 6 meters. Okay? Anything above this? Okay. So anyway, so now to go for next session, it will take, means next concept, that is classification of colloids. It may take more time. So what I will do is, I will stop here for today's this one. So while coming tomorrow, you can thorough with colloids, definition of colloids. Then before that, nature of the enzymes and lock and key hypothesis. And try to solve, whether you people have solved in text question 5.4, 5.5, 5.6. Yesterday I had asked you people to solve those questions, find the answer for them. Okay, so anyway, whether you people have done, fine. So I will stop here. Tomorrow we'll start with the types of colloids. Okay, so tomorrow we're going to start with the types of colloids. Thank you. Take care.